Hello everybody, welcome back to the online course on embedded system design, verification and test. Okay, in last class we have discussed how to represent an transition system with the help of an ordered binary decision diagram. Okay, now today we are going to see about the symbolic model checking. We already have discussed about the model checking algorithm. In symbolic model checking algorithm, we are going to implement the same algorithm, but we are going to use data structure BDD to represent the transition system as well as set of states. Now, we will see how we are going to look for the correctness of a given CTL property in a BDD representation of the transient system. Okay, already we know that for model checking, we should have a model which is some sort of your finite state machine, and we are having a CTL property, and when we are going to look for the correctness of this particular CTL property in the given model, then the model checking algorithm returns as the set of states where the given CTL formula is true. Okay. Now, already we have seen that ROBDD can be used to represent the transition system, okay, because we are dealing with a transition system which is a finite state machine with additional property which is basically says about the leveling function, and we know how to represent all those things. So, this transition system can be represented with the help of ROBDD. Similarly, if we are going to consider a set of states of that particular transition system, then that set of states can be represented with the help of an ROBDD, reduced ordered binary decision diagram. So, these are the two bases that we have in our hand. Now, we are going to use these two things to implement the model checking algorithm. So, which will be known as symbolic model checking. So, what is a model checking algorithm? We know that it is a graph traversal algorithm, and if you look into the operators, so whatever operators we are going to say, if it is a there exist x, say next state p holds, there exist a path, next state p holds, or in all path in future p holds, or maybe there exists a path where p remains true until q becomes true. Maybe these are the three basic operators we can consider, and if we are having algorithm for these three methods, then other methods can be expressed in terms of these three operators. Now, when we are looking for the implementation of these three operators, it is nothing but a graph traversal algorithms. And what is the crux of this particular graph traversal algorithms? Just we need to find out the predecessor states of a given set of states or a given set. Okay. So, if I am having some states like that, then in my transition system, I may have some scenario. So, if say in this particular state say p is true, then there exists a path in next state p is true, then we have to find out what are the predecessor of those particular states or this set of states. So, this is the basic notions that we have to find out the predecessor state of a given state or a given set of states. So, this is next operator. For future and until operator, we have to do this job repetitively until and unless we are going to get a fixed point. That means, there is no more addition of a states in that particular set of states. At that point, we terminate. Okay. We terminate our algorithm. So, the basic crux is to find out the predecessors. Now, already we have seen that how to find out the predecessor states. So, we are having or we define two operators, one is a pre there exist and pre for all. So, pre there exist x, where x is a set of states. So, pre there exist says that at least we are going to look for those particular states, at least one transition is coming to the state of states or coming to a particular state which is a member of this particular state x. Okay. Or for all x, that means we are going to look for those particular states where all the transition will lead to a next stage which a member of this particular subset x. Okay. So, if this is the scenario, then for dr exist, we are going to get both the state S1 and S2, but for all we are going to get only S1 because all the transition are coming to a stage which is a member of this particular x. Now, our job is to, if I am having this particular set of states, now I have to find out what are the predecessor of this particular state satisfying those particular properties. For dr exist x, it should satisfy this property, and for all it should satisfy this particular property. So, our job is to find out this particular set of states which are predecessor of this particular set of states. Now, if we are representing our transition system with BDDs, now we have to see how we are going to get those particular predecessor states. So, we are going to look for those particular scenario. Again, we have seen one important relationship between pre-dr exist x and pre for all x. So, this is the relationship we have seen, that pre for all x is equal to s minus pre dr exist s minus x, where s is the set of all states. In a transition system, we are having several states, we are going to consider all the states and we say this is the set S, and x is a subset of S. Then from that we are going to find out what are the predecessor of those particular states which belong to x. So, if we are having a method to find out pre-dr exist x, then we can use this method to find out pre for all x, and we will use this particular relationship. Now, we are going to see how we are going to find out or have a method for pre-dr exist x. Okay. Now, this is a simple method that we are going to say what is the procedure for pre-dr exist x. We are going to have the set of state x which is a subset of given set S, okay, and we are having a transition relation. Okay. Now, we are going to represent the transition relation with the help of BDD, and we say this is the B arrow. So, B arrow is the BDD representation of the given transition system, and Bx is the BDD representation of the set of states x. Now, in the procedure we are having two steps. In the first step, we are saying that rename the variable in x to their prime version call the resulting BDD as Bx prime. So, basically what will happen? To represent all the states, so we are taking help of some variables, say this is the variable set x1, x2, xn. If we are having total 2 to the power xn 2 to the power n states, then we need that many variables. Now, if I am having a transition from one particular state, say Si to Sj, then we are representing this transition like the order pair Si Sj. So, Si will be represented by the state variable, similarly Sj will be represented by the state variable. To represent the next state, we use another set of variable which are nothing but the prime version of those particular variable, that means x1 prime, x2 prime, xn prime. So, this transition relation will be represented by x1 to xn and x1 prime to xn. So, these are a variable that will be involved while we are going to represent this particular transition, like all transition will be represented by these things. Now, Bx is the OBDD representation of a particular state or a state of states. Okay. Now, what will happen? We will just rename the variables of this particular BDDs. Now, what is the effect? You just see, if I am going to have the scenario like that, if I am having a Boolean function f is equal to say a b plus say b c, and if I write the same expression f is equal to say x y plus y z, then both these Boolean expressions are going to represent the same function, because what will happen here in one expression I am writing x, but this x variable is represented by x, in the other one b it is renamed by y, and c it is renamed by z. So, you just see whatever we are having, these variables are nothing but some sort of placeholder which can take values either zeros and 1. So, variables can be different, but the functional values will be same. So, we can have similar scenarios. So, this function can be represented with the help of an BDD or in particular OBDD. So, we are going to get an representation which is basically BF. Then for this function also we are going to have the same BF, provided we are using the same variable ordering. The variable ordering should be A, B, C for the first equation and x, y, z for the second equation, because we are having this particular mapping. So, if we are having the same variable ordering, basically with respect to their corresponding mapping, we are going to get the same BDD. So, now what happens, we are having Bx, which is a BDD representation of the state of states, and it involves the variables x 1, x 2 to x n. Now, we can rename those particular variable, okay, but still our BDD representation will remain same. Okay. That means, I am going to say that x 1 is replaced by x 1 prime, x 2 is replaced by x 2 prime, similarly, x n will be replaced by x n prime. So, we are going to have the same BDD. So, in that particular case what will happen, I say this is the BDD B x prime. Okay. Now, consider a small transition diagram, or maybe say one finite state machine. So, if I am going to consider this particular set of state x, okay, these states will be represented by variable x 1, x 2 and x n. Okay. Now, this BDD, whatever BDD I am getting over here, I am going to say this is Bx. Now, I simply rename those particular variable by its prime version, and we are going to get the BDD Bx prime. Okay. That means, if we are having this thing, that same BDD we are representing this particular state of state, but we are taking the next state variables. And now, we want to find out the predecessor of those particular set of states. Okay. Then what will happen? What is the predecessor? I must get these two things. Okay. Now, what is the relationship? I am having those transition. This is basically S I to S j, if this is say S I and S j. Now, why we are doing that renaming? Now, you just see this transition, I have to concentrate on this transition to find out the predecessor of this particular state S j. So, this transition is represented by present state variable and next state variable. So, that is why we are saying we are renaming the variable of this particular state, it is by next state variable, and now the other state S j now will map to this particular B x. We will see how we are going to map these things. Basically, we are going to look for this particular transition and going to have a predecessor of this thing. So, since we are concentrating on these things, that means this transition has to be represented by its state variables. So, in this particular case, these state variables are basically now prime version, and this state variable is my predecessor version. Okay. Now, with the help of this renaming, we try to find out the predecessor state. Now, how we are going to do it? Now, we are going to say that compute the OBDD for exist x prime apply dot B arrow, the BDDs of the transition system, and B x prime using the apply algorithm and exist algorithm. So, when we are using this particular apply algorithm, we are using two BDDs. BDDs for transition system and BDDs for the set of states. Okay. Now, when we are going to apply this particular apply algorithm or use this particular apply algorithm, then both Bx prime or B arrow must have the computable variable ordering. That means, they are going to use the same variable ordering. So, for B arrow I may think that it is the variable ordering x 1, x 2, x n, x 1 prime, x 2 prime, x n prime. Maybe this is the variable ordering that I may have for B arrow. Then the variable ordering for B x prime will be your x 1 prime, x 2 prime, x n prime. Okay. Now, they are having the computable variable ordering, but B x prime is independent of those particular variable x 1 to x n. So, this is the scenario now we are having. Now, we are going to use the apply algorithm and see what is the result that we are going to get. Now, consider such type of scenario. And so, we are considering that this is the state x, x is the set of states. Okay. Now, we are using that particular B x prime to represent this particular set of states, and B prime is the B arrow is the representation of this particular entire state transition graph. Now, when we use this particular algorithm apply, then what will happen, you just see, it is going to have an product of this entire state transition system and this particular B x prime. Now, while after applying this thing, it is going to give me an BDD. That BDD is going to involve all the variables x 1 to x n and x 1 prime to x n. Okay. This is going to have these things, and basically if you see what we are going to get in this particular case, we are going to get basically those particular transition, because we are going to look for the there exist states. Okay. So, basically it is returning these particular transitions. Okay. Now, these all those transitions are having variable form x 1 to x n and x 1 prime to x n prime. So, I am getting an OBDDs which are having the ordering x 1 to x n and x 1 prime to x n, which basically returning us all those particular transition. Okay. Now, from those particular transition, our objective is to find out the predecessor states, where from this transition is originating. So, for those particular transition, that present state is represented by the variable x 1 to x n, and the next state is represented by x 1 prime to x n prime. Now, we are going to use this particular exist algorithm on this particular x prime. Now, what is this x prime? It is nothing but the set of variables x 1 prime, x 2 prime, x n prime. That means, we are going to apply this particular exist on the resultant BDD on all the variable of x prime. That means, we are trying to relax the constraint on those particular variable x prime. So, when we are going to relax the constraint on the x prime, then the resultant BDD is going to have the variable only x 1 to x n. Okay. Now, what we are considering? We are considering all those particular transition, and now we are relaxing on the next state variable. Now, we are going to get an BDD which have only the present state variable. That means, the resultant BDD is going to represent this particular state of states y. Okay. So, this is the inherent meaning of this particular operation and this particular pre-dr exist x method. Okay. Now, from here what we have seen that we can find out the predecessor states of a given set of state using this particular pre-dr exist x. Okay. Now, whatever BDDs we are getting for this particular set of states y, it is an OBDD and it is going to have the same variable ordering. The variable ordering will be your x 1, x 2 to x n. Okay. This is the way that we can look into it. Now, the resultant BDD may not be a reduced one, then we can use those particular reduction techniques that we know we are having only 3 reduction technique. We can use those particular 3 reduction technique to get the ROBDD out of it. Okay. Now, what we have seen that if we are giving the transition system or representing the entire transition system with the help of an OBDDs, we are considering a set of state of that particular transition system and representing those particular state of state with another OBDD, but the variable ordering of both the OBDDs must be computable. That means, they must have the same variable ordering. Then, after application of these two operations, apply and exist, we are going to get an OBDD which indicates the predecessor state of the given set of states. Okay. So, now we are having a method to find out the predecessor state of a given set of states, which basically says that pre-dr exists. That means, dr exists at least one transition which are coming to this particular set of states. Now, we know the relationship between pre for all x and pre-dr exist x. So, now we can use those particular relationship to get the pre for all x also. Okay. Now, we are having a method how to find out the predecessor state of a given set of state. Okay. Already I have explained the method with example. So, we are having an BDDs or basically say OBDD B arrow for a state transition system. We are having an OBDD Bx for set of states. Okay. So, x is a subset of the entire states S. Then, with the help of these two BDDs, now we can find out the predecessor states of this particular set of states. Okay. Now, just see, we are going to look for the now model checking algorithm and see how we are going to have a symbolic implementation. In symbolic means, we are going to represent or going to use OBDDs to represent the entire systems and the set of states, and it says that we are not enumerating the set of state, but symbolically we are representing with the help of BDD. That is why the term symbolic is coming into picture and it says symbolic model checking. Now, what is the CTL model checking algorithm? Simply look into it. For operator exp, there exists a path next that p holds. Okay. So, we know the method. It basically says that first we are going to take all the states, set of states where p is true. Then we are going to collect those particular states as 0 belongs to x such that it satisfies this particular property. From S 0, there must be one transition to S 1, where S 1 belongs to x. Okay, already we have seen this particular algorithm and finally, we return y. So, how we are going to represent, going to have an implementation for this particular method symbolically. So, this is the symbolic representation or maybe symbolic model checking algorithm for there exists a path in next state some formula phi true. So, in that particular case what will happen? We are going to take the BDD B phi, it says that set of states where phi is true. Okay. Now, we are having a CTL formula phi. Now, we know the set of state where phi is true. So, we are going to collect those particular set of states and going to have a PDD representation of it, and I said this is your B phi. So, this is analogous to x equal to set of phi, the way we are saying this particular statement. Okay. So, this is analogous to this particular statement of the model checking algorithm. Now, B arrow is the OBDD representation of the transition relation or entire transition system, and now B phi and B arrow must have computable variable ordering. Now, after that we are just using this particular operator pre dr exists B phi. B phi is the BDD representation of the states where the formula phi is true. Okay. So, it is analogous to like that we are going to look for the predecessor states as such that from S we are having a transition to S dash and S dash belongs to X. This is the predecessor operator basically does. So, finally, we are going to return this particular thing, and what it is going to return? It will return a BDD. That BDD is going to basically talk about or going to represent a state of states which is having a transition to this particular set of state X, or basically these are the state of states where the formula E x phi is true. So, basically now we can think something like that. We are talking about E x phi. So, consider a small transition system. Now, just say these are the states where phi is true. That means, I am going to get this particular set of states, and I say this is basically B phi, this is the starting point, and I am going to have the BDD representation of this particular entire state space, which I say this is your B arrow. Now, we apply this particular model checking algorithm, then what will happen? It is going to give me those particular states where the next state phi is true. So, in this particular case, it is going to return me those particular state, maybe this is S0, S1 and S2. Okay. Because in this particular state, the next state phi is whole. For here also at least I am going to have one state. So, after performing this operation, it is going to return me this particular set of state S0, S1, S2, where this particular formula E x phi is true. So, this is the way I can look into it. Now, I am having the implementation of this particular E x operator. There exists a part in next state phi holds, where we are using the BDD representation only, BDD representation of the transition system and BDD representation of the set of state. Now, similarly, the another operator is your AFP. There exists a part, AFP says that in all part in future we are going to some state where P is true, and this is the algorithm that we are having. First, x is equal to s, that means I am going to take the entire state space, and y is equal to set of P, where I am going to take the set of state where this particular atomic CTL formula P is true. This is the satisfaction relation. So, I am going to consider all the states where P is true. Now, repeat until x equal to y. We are going to repeat it like that when x become equal to y, and initially I am going to mark x is equal to y. That means, wherever that P is true in that particular state, AFP is also true, because this is as per the notion of our time future includes the present scenario also. So, this is the initial state where that AFP is true, then I am going to collect such type of state and going to append with y or union with y. What those particulars must have this particular property for all S dash we have a with the transition S to S Z, we must have all S Z must belongs to Y. That means, if here AFP is true, then necessarily AFP will be true over here also, because all the transition is coming to a state where AFP is true. So, this is the scenario. Now, we have these things will be again implemented with the help of symbolic model checking algorithm, where we are going to use the BDDs. So, similar to your EX phi, here I am going to say that B phi is an OBDD representation of the state of state where phi is true. This is analogous to Y is equal to satisfaction of phi. B arrow is the OBDD representation of the transition relation. Okay. So, one I am taking B phi, these are the state of BDD representation of the state of state where phi is true. B arrow is the BDD representation of the transition system, and Bx is the BDD representation of the all states of the system. So, one is your transition relation and Bx is the all states. This is the BDD representation. So, this is analogous to your x equal to s. So, these are the three things I am having, x equal to x and y equal to set of p. Now, what we are doing, repeat until Bx equal to B phi, that means BDD representation of the set of state where phi is true will be equal to the previous iteration basically. Now, here first step we are going to assign B phi is equal to Bx, that means we are retaining the state of state where phi is true, because we are going to append states to this particular set of state y. That means, we are going to append state to this particular state or to this particular B phi. Now, what will happen? Now, B phi will be, now we are going to modify it. How we are going to modify it? Apply pass B phi and pre for all B phi. Okay. So, this is analogous to that we are appending y with y union and all such type of states which satisfies this particular property. So, we are using now pre for all, and we know that pre for all can be captured by this particular relationship pre for all x equal to s minus pre there exists s minus x. So, we are having a method to this thing. So, this is plus is going to have the union. So, we have used this particular apply method or apply algorithm to get the union of these things, and we are going to repeat it until unless that previous states or set of states is equal to the set of states that we are getting after this iteration. So, once these two BDDs become equal, that means we are not adding any more new states to it, and we terminate it, and finally, we return this particular B phi. Now, B phi is the BDD representation of the state of states where this particular A f phi is true. We are looking for the formula A f phi. So, we are getting an ordered BDD representation of the state of states where this particular formula is true. Now, after that we can use those particular reduction technique to get the ROBDD representation of those particular state of states. Now, this method is giving us the returns the state of state where this particular formula is true, and it gives me the BDD representation of those particular set of states. Okay. Now, we are having another operator called E until. Okay. So, P until Q or there exists a path P until Q. So, this is the method. Now, what we are doing? Going to take the set of state where P is true, we are going to take the set of state where Q is true, and we are going to look for entire states, all the states of the system. Okay. Now, we are repeating it until x equal to y, then we are going to these things. Now, in y, these are the state of state where Q is true. Now, we know that where Q is true, then E P until Q is true according to our notion of time, where we says that present or future includes the present behavior also. So, wherever Q is true, then E P until Q is true. So, that is why this is the initial state of state where E p until q is true. Now, x equal to y, now we are retaining the previous set of states. Now, here this is the operation that we generally perform, already we have discussed in our model checking algorithm. So, y union, and what sort of state of states we are going to take? We are going to consider those particular state of state. We are going to collect those particular states which is going to satisfy this particular property. That means, at least there is one transition to the set y, and after that intersecting with w, that means where p is true. So, we are going to look for such type of scenario. If say E p until q is true over here, E p until q is true over here, and say it is p is true over here. Then, when I am going to take the predecessor state, we are going to look for those particular predecessor state where p is true. That means, this particular state will come into picture, because this is the w union, and what is w? Where the set of state where p is true. So, this predecessor will come, but this predecessor will not come into the picture. So, this is the way we generally collect the set of state where p until q is true, and we repeat these things until and unless we cannot add any more new state. So, this is the represent symbolic model checking implementation, where we are using the ordered BDD. So, this is B psi 1 is the BDD representation of the state of state where psi 1 is true, and B psi 2 is the set of state where the CTL formula psi 2 is true. So, these are the two BDDs we are having. Then we are going to take another BDD Bx, which is going to BDD representation of all states, okay, and B arrow is the BDD representation of the transition system. Now, all those 4 BDDs must have computable variable ordering, then only we can perform the operation. So, it says that Bx is the OBD representation of the system. This is analogous to x equal to s. If you compare with the our model checking algorithm, this is B phi 1 is the OBD representation of the set of state where psi 1 is 2. This is analogous to w into set of psi 1. B psi 2 is the BDD or OBDD representation of the set of states where psi 2 is true. So, this is analogous to y is equal to set of psi 2, and B arrow is the OBDD representation of the transition relation. So, these are the 4 BDDs we are using. Now, repeat until Bx is equal to P psi, which is analogous to your x equal to y, and here you say that initially wherever that psi 2 is true, we are assigning to Bx. Okay. So, again you just see that whenever we are going to have E, there exists a path psi 1 until psi 2, all the state where psi 2 is true, in those particular state we say that E psi 1 until psi 2 is true. That is why this is the initial set of state or BDD representation of the initial state of state where psi 2 is true. Now, we are going to collect more and more state. So, what is this? So, this is the scenario. First, we are using this particular apply dot to B psi 1 and these things. So, this is basically B psi 1 is the set of BD representation of the state of state where psi 1 is 2. This is equivalent to this W, okay, representation of the set of state W, and this is the intersection of such type of states. So, that is why for this intersection we are using this particular dot operators. So, B psi 1 pre there exists B of psi 2, okay, taking all the states like that previous example, all the taking predecessor states where the E p until q is true and p must be true over here. So, this is W intersection of these things. So, this is dot operation is there, and we are going to add those particular things to the state of state where already we have found that E psi 1 until psi 2 is true. This is the union. So, this union is again given by this particular plus operator. So, we have applied or use this particular applied method twice to find out B psi, and we repeat these things until and unless it is going to satisfy this particular property. Then finally, we are going to return B psi 2, where this particular formula E psi 1 until psi 2 is true. Now, you just see this is the symbolic implementation, or I can say that where we have used the BDD representation for the entire system and the state of states to implement the operator E psi 1 until psi 2. Okay. Now, what happens? We have seen these things for EXP, AFP and EP until Q, and we know that if we are having a implementation of these three operators, then other operators can be converted or can be written with respect to these three operators. So, now we have a method where we have used the BDDs to find out the state of state where a given CTL formula is true. Now, when we are using OBDDs or say ROBDDs, up to some extent we able to contain the state space explosion problem, because in many cases it is observed that the OBDD representation of the entire system or maybe set of state coming to be a very small one if we can find out a proper variable ordering. So, we use defined heuristics initially to find out the appropriate variable ordering, and once we get the appropriate variable ordering, then we use this particular variable ordering to represent our entire state space as well as the set of states. So, when you use this particular symbolic method, symbolic model checking, we can take care of many more states. Okay. It is at least getting better result with compared to the graph based algorithm or graph traversal algorithm. So, that we have the implementation of model checking algorithm with BDDs. All right. Now, what are these things? So, whatever we said, this is the in nutshell I can say that BDDs are used to represent the transition system and set of states, or in particular I can say it is the ordered BDD, because we are using several BDDs and we are performing operation of several BDDs. So, they must have a computable variable ordering. So, we are using ordered BDDs to represent transition system and the set of state. Use of ordered BDD helps to contain the state space explosion problem, because already I have mentioned that in many times or many cases we are going to get a compact representation of those particular set of states and the transition relation, but main thing is that we have to get an appropriate variable ordering. So, here already I said that variable ordering plays a major role in the size of the BDDs. So, we use some heuristic to choose the proper variable ordering. So, these are the basic points that we have to keep in our mind while we are going to implement the model checking algorithm symbolic way. That means, we are going to use the OBDDs to implement our model checking algorithm. Now, along with that, in model checking what we need a temporal logic. Okay. And in this discussion we are using a particular temporal logic which is called CTL computation tree logic. And what are the temporal operators we are having? Basically, we are having the next state, global, future and until. And for CTL, all those temporal operators will be preceded by a path quantifier. We are having two path quantifier A and E. A is for all path, E is for here exists a path. And when we preceded those particular temporal operator with path quantifier, then all becomes a state formula. That means, we are specifying the properties of the system in a state, and CTL model checking basically taken care of the state formulas only. And whatever operators we have discussed till now, that X, G, F and U, here if you look in the notion of times, these are qualitative in nature. What we say? AFP, whether in all path in future P holds. That means, we are going to look for all the transition from a particular state in such a way that somewhere in future or eventually we are going to get a state where P is true. So, this is qualitative in nature. We are saying that in future we have to get it. Okay. And similarly, if I say that E P until Q, what we are saying that P must remain true, eventually Q becomes true in a particular state, in a particular execution or in a particular execution trace, because it is taking for E path quantifier. That means, we are not concerned about all the path, but at least in some path P must remain true until Q becomes true. Again, it is qualitative in nature. We are not having any quantity. We are not saying that in all path in future within 5 units of time P must hold true. So, that will be quantitative in nature. So, how to look for the quantity of time? So, quantitative in nature. That means, I can say that I am looking for some property to hold within say 5 unit of times or maybe in between 7 to 10 unit of times. So, these are the time notions. So, along with the temporal operators we can give the bounds also. So, once such logic is developed, we say, and this logic is called RTCTLs. This is real time computation tree logic. So, once such logic is there, RTCTL, where we say that time will be specified in quantum. Okay, that means, it is quantitative in nature. Whatever algorithm we have discussed, this is qualitative in nature, but now we are going to specify a quantum of time. So, we are going to say that the time will be quantitative in nature, which is very much required in a real time system, because always we want to have the response within a specific time. So, with the CTL operators or temporal operators, we can give a bound to indicate the quantum of time. So, for that what will happen? All those operators will be given as some bounds. So, x is basically next state, we do not have any problem. If we are having a state in the next time, it should get it, but for G globally, whether we are going to look for all features or we are going to bound it to some times. So, it will be something like that, either looking into some bound y. So, within this y, all states should satisfy this property, or in some notion it says that from current time present state to that particular bound y. So, we can have the subscript bound 0 to y, or we can say that less than y, that means from this particular state to the time instance y. So, similarly, in future we can say that within this particular y time unit, that P must be true or that given property must be true, or we can give a bound that in between x and y it must be true. That means, if I look into transition path, then if I say it must be less than equal to y and say this is the time instance y, that means from this particular state somewhere P must be true if I am going to look for say AFP or EFP, or if I give a bound like that x and y, then P must be true within this particular bound. So, both are possible. Similarly, in case of until also I can give a bound, or you can say that less than equal to y. So, within a range or maybe the total bound from the current state to this things. Now, this is the way we can have the quantitative in nature, we can implement or we can indicate a quantity. So, those algorithm, whatever model checking algorithm we have discussed, those can be implemented to take care of those particular bounds also. We are having the implementation. So, in RTCTLs, real time computation tree logic, we generally provide such type of bound, and we say that within some specific time my given property should hold. So, such type of reasoning can also be done if we are going to use those particular bound or use the RTCTL. Now, what is the basic restriction or limitation of this particular RTCTL? Here the bounds basically takes integer values only. maybe we can say that within time period, time stamp 3.3 and 5, or maybe within 10 time units. So, it can take integer values only, but now people are looking for the handle real time also. So, for that we are having one logic called TCTL, time CTL. So, in case of time CTL, then what will happen? We are trying to consider the real numbers also as a bound. Maybe we can give 3.5 or say 7.35 like that, but the system becomes more complex when we are going to handle real time, because you can see that if I am having a transition, maybe in quantum of time I can say this is in one time unit, it can come to the next state. Okay. So, now when I go for the real time, then what will happen? I can say that within 0.5, maybe 0.25, all those particular states will come, on all those particular behavior you have to take care of it. So, this is why that we are going to have a time region, and people have come up, researchers have come up with a method where we can handle the real number also as time, but system is very complex. Okay. So, it is, we are not going to discuss those particular methods or particular issues in this particular lecture. Just I am giving an idea that we can handle time, quantum of time may be integers, and quantum of time may be your real numbers also. So, if you are interested, then you can have a look into those particular research paper where people have introduced TCTL. Now, what we have discussed till now, here you see that we are going to design a system, then we know the behavior. So, when we are going to design a system, we know the behavior of the system, how it is going to behave. Okay. So, that means it is that system is having different configuration. That configuration is basically nothing but the combination of those particular state variables, and we are having several transition from one state to the other state. So, if a particular instance, if we are doing some activities, then it should lead to some result. Most of you might have seen the coffee vending machine. If you use the coffee vending machine, then what will happen? You go to the coffee vending machine and you press the button coffee, then what will happen? It will take the premix of the coffee, it will bring it out, then it will mix with your milk, and finally, it will give it to the coffee, ready-made coffee in your cup that is placed inside the outlet. In the same machine, if you are going to press the button tea, then what will happen? It will take the premix of tea, mix it with water, and finally give you the tea. So, how we are going to control all those things? So, when I press coffee, then what will happen? I have to open the valve where I have kept the premix of the coffee. When I press the tea, then it must open the valve where we have kept the premix of the tea. Now, you just see that means in one particular state, the coffee, valve of the coffee is on, but tea and other stuffs are off. So, this is a particular configuration where I am going to make coffee. So, another configuration I am going to get where the valve for tea is open, but the valve for others items are closed. So, this is the another configuration, and we are having transition from one to the other depending on the way we are going to use this particular coffee vending. So, this behavior we are going to capture in our design, and generally we are going to get a finite state, and most of the cases we are going to use the finite state machines. And here in model checking, what happens? We say it is a Kripke structure because it is having two more criteria need to be satisfied. One is that whatever transition relation we have, it must be complete. That means, from all state there should be an next state also. And secondly, we are having a labeling function. With the help of labeling function, we are going to say what are the atomic proposition 2 in a particular step. So, this is formally we are capturing our design. Then we know that whenever we are going to design it, it must satisfy some property. Okay. So, in that particular case, those properties we are going to capture with the help of CTL, because in this class we have discussed about the CTL model checking only, but you can look for some other verifier also where we can specify the property in some other way. So, these are the two things, because we know my system should behave in this particular way. So, that behavior we are going to capture with my CTL, which is a property of this thing. Then we use the model checker to check whether this property holds in this particular model or not. So, if property is true in my model, then what will happen? That model verifier is going to give me the answer yes. So, if all the properties are true, then what will happen? I can go for the implementation of my design. Okay. Now, if some of the properties are not true, then what will happen? That model verifier will say that whatever system you have designed, it is not satisfying some of the properties. Along with that, it will give me one indication, or you can give me a trace to show that if you follow this particular execution trace, the given property is false. Then as a designer, what I can do? I will concentrate on those part of my design to rectify those particular errors, and finally again I am going to look for re-verification. Once it is correct, it is give me some confidence that whatever I have designed it is correct, then I will go for the next phase of my design, or next phase of or design phase where I am going to implement this particular design. So, this is the steps that involve when we are going to design it. Now, when we are coming to the embedded system, basically what we have seen, embedded system is nothing but a combination of hardware and software. That means, we are going to design a system where both hardware and softwares are involved. That means, some part will be implemented in hardware and some part will be implemented as a software program. So, when I am going to design a system to fulfill some of my criteria, some of my requirements, then we are going to identify what are the different tasks that we have in the system, what are different tasks we need to perform, and for every task we are going to have the modules. We say that these are modules that we need to implement to get the solution, to get the final product. Now, after having those particular tasks or particular module, now we have to identify what are the modules that we are going to implement in hardware and what are the modules we are going to implement in software. If you are going to implement everything in hardware, it is fine, but why you are looking for both the option, going to implement something in hardware and going to implement something in software? Just to meet all our requirement. One is that we are having some performance criteria that my system should respond well, behave within specific time, which is basically the performance. Another criteria we are having that cost factor, it should remain within my budget. It should not exceed my budget, because if it exceeds my budget, then my product will be very costly. So, for that now we are going to identify those modules where the module is your performance incentive. That means, it should work in a faster way. So, for those basically we are going to select for hardware implementation, because if you directly implement something in hardware, then it will work faster or response will be very good. Now, other component where it is not that effective, that we can devote time sometimes to get the responses, but we are going to cut the cost or reduce the cost, then those components we will identify, and we say that for them we are going to have an software implementation. That means, that software will be used some resources, common resources to execute that particular software. So, this is the way we can look into it. That means, we have to identify the hardware part and we have to identify the software part. Now, what we are going to do? We are going to design each module the way already I have mentioned and get the abstract model of those particular modules. That means, we are going to have a formal representation of those particular modules, and we said this may be some sort of a finite state machines. Then identify the specification or properties to be satisfied by each module. Now, we know what is the requirement of each module, what are the tasks it needs to satisfy, perform, or what property it needs to satisfy. We are going to identify those particular specification and properties for each and every modules. Then what we are going to do? We are going to use our verification techniques to check for the correctness of those particular properties. Once you get the confidence that yes, whatever I have designed and whatever requirements I have specified, that my design is going to meet all those particular requirements and properties. Then what will happen? Next we move for the implementation. So, generally what will happen? For hardware component, we may use some hardware description language like your Verilog or VHDL, and we are going to get the implementation of those particular hardware component. Then we can simulate it, we can look for the testing it, then finally we are going to implement it in our silicon. And the software programming, for software component we are going to, we may use some programming language to implement those things. On the other hand, also sometimes what will happen, for some small system, people come up with the initial design and they wrote the modules for hardware component, they wrote the modules in your hardware description language like Verilog and your VHDL. Software component, they use some programming language to implement, maybe C, Java, Python, etc. Then if it is a small system, then what people used to do from those particular implementation, they try to extract out the models. Okay. Already I think I have mentioned that we are having mechanism to find out the behavior or find out the model, and on those particular model people used to apply the verification to check for the properties. This is basically for small system, we can go this way also, but for bigger system generally we first verify our design, then we go for the implementation. Okay. Now, we have seen how to look for the correctness of a system that we are going to design. Okay. So, for that some of the tools I am just going to mention it. If you are interested, you can look for it. One is your CUDD. This is a binary decision diagram package developed at your University of Colorado at Boulder. So, CUDD is a BDD manipulation package. So, this is a for academic purpose, it is available. Okay. It is a shareware. So, if you are interested, you can download it and you can see how you can use these things for your construction of BDD or manipulation of BDD for some Boolean function. Another one here, new SMB. SMB is your symbolic model verifiers. This is new SMB is the extension of SMB where we are having now more features. So, this is the first model checker based on BDD. Okay. So, this is also available. So, if you are interested, we can look for, or you can download it, install it and see how system will be specified in this particular new SMB, how the properties will be specified, then how we are going to check the, while you are going to check the correctness, then what are the outputs that we are going to get. You can look for it. Another one which is the bounded model checker. This is some sort of bound is specified in the model checker. That means, while I am going to look for a particular execution trace, how long I am going to explore the system. Okay, this is because we have to say this thing. So, this is going to specify some bound. So, it is also a model checker only. Another one which is using spin, this is a LTL model checker. So, basically we are discussing about CTL, computational tree logic, computation tree logic, and we have seen the algorithm how to check those particular formulas. But LTL is another temporal logic which is your linear time temporal logic. So, we are having a model checker called spin which take care of LTL. Now, what is the difference between CTL and LTL? In case of CTL, you just see it is a state formula. In case of LTL, it is a path formula. This is the basic difference. So, the truth values of CTL will be defined on a state of the system, but truth values of LTL will define over a path in the system. So, this is the difference. So, with the LTL also you can specify our property, and we are having a model checker for LTL properties which is known as spin. So, if you are interested, you can just look for those particular tools and see how you can use those particular tools during your design phase. Okay, with this I conclude my lecture here today. Thank you all.